Hello everyone. Hope I am audible. Hello. Hello. Hope I am audible to everyone. Netra, can you kindly confirm? Hello. Okay, let's start today's session. Welcome to week five's discussion session. So here I will be talking. I will be discussing the previous year's assignment for week five, and in the meantime, if anyone of you comes with any problem, we'll be trying to solve that too. So let's begin. Okay, first, fine. So the first question is, what is the frequency of a ring oscillator with 50 inverters given? Resistance is 1 kilo ohm and capacitance is 1 femtofarad. Okay, so let's look into it. First of all, uh, if given an inverter, chain of inverter, let us consider there are n such inverters. Then, if we look into the circuit of of this chain, we'll see that and and so on. Okay, so basically, there will be two capacitance systems, one due to this one 3C, another due to this one, so another 3C. So net will be getting 6C. So the t propagation delay uh, will be for any transition 0 to 1 or 1 to 0 for one inverter would be equals to, the normalized one will be equals to 3RC plus 3RC divided by 3RC, which will be equals to 2. And the output that we will be getting will be of such kind of output we will be getting from the ring oscillator. And maybe we can call this as the t propagation delay 0 to 1, and this one is the t propagation delay 1 to 0. So similarly we will be getting another propagation delay term, okay, we will be getting another propagation delay term which will be equals to t propagation delay 1 to 0 for one inverter, which will be equals to same 3RC plus 3RC by 3RC, which will be equals to 2. Therefore, uh, the t propagation delay net will be equals to t propagation delay 0 to 1 plus t propagation delay 1 to 0 for one inverter, which will be nothing but 2 plus 2 equals to 4. Now, if there are n number of such inverters present, my net t propagation delay would be coming to 4 into, for n inverters it will be, it is one inverter, it will be coming to 4 into, sorry, 4 into n, correct? And now the net time period that will be acceptable will be equals to 4n into uh, r into the capacitance. The capacitance is coming as 3C, right? So it would be 12 nrc. Therefore the acceptable frequency f would be equals to 1 by 12 nRC. Now we can see n is given as 15, r is given as 1 kilo, and c as 1 femto. So it will be 12 into 15, sorry, so it would be 12 into 15 into r is 1 kilo, 1 kilo, and other one is how much? It is 1 femto, 10 to the power minus 15. So if we solve it, it will be 10 to the power 12 by 180. So it would be coming as 5.55 gigahertz. So the answer is 5.5 gigahertz. Okay, 5.55 gigahertz. This one is the answer. Correct? Okay. Fine. If I can minimize it. Fine. Okay. Next, let's move to the next question. Question number 2. I hope the first one is clear, right? I hope there is no confusion. Okay, fine. Let's move to the next question. Okay, choose the correct option about the statements. First one is logical effort of a 3-input NAND gate in long channel current model is greater than the same in short channel current model. Now, what is short channel effects? What does it lead to? Always remember that all the short channel effects leads to an increase in current than the expected value, be it dibble or be it any other thing, threshold voltage lowering. All these things leads to what? It leads to more current. And if you remember the first class that I taught, I told that a simple definition of delay can be written as T is charge per unit current. Okay, current is basically charge per time, so we will see that the units are matching. So a simple approximation of delay can be estimated by simple division of charge by current. So if by anyhow my current is increasing, I can say my net delay would decrease. Okay, and as short channel effect leads to more amount of current, so the short channel devices would suffer or would experience a lesser amount of delay. Okay, that's simply it can be understood by this logic. Okay, and for more detailed explanation, let me write the expressions of logical efforts for this NAND gate and NOR gate. Logical effort for long channel device, logical effort I am writing as G. Okay, for 3-input NAND, it will come as, it is n plus 2 by 3, and as n equals to, for 3 input, so n equals to 3, so it will be 3 plus 2 by 3 equals to 5 by 3. And logical effort for short channel device, 3-input NAND would be, it is basically, if you can remember, it was something as x plus 2 by 3, where x, the expressions are as derived in the class, it was something as 0.7 plus n into 1.04 by 1.74, where 1.74 was the V critical, right? So I'll be getting excess, how much? I think it was 2.18. So my G would become 2.18 plus 2 by 3, 4.18 by 3. Okay, so it would become, my G would become for short channel 4.18 by 3. And you can see this one is how much? This one is 5 by 3, this one is 4.18 by 3. Therefore G short channel is less than G long channel for 3-input NAND. Okay, so first statement is true. Second statement, logical effort of a 3-input NAND gate in long channel current model is lesser than the same in short channel current model. So if first one is true, second one is false. Correct. Now third one is given regarding two input NOR gate. What is the expression for two input NOR gate? The next question is regarding the same, so I'll be deriving the expression there and then we'll be getting the answer. Okay, but from the first logic that I mentioned, that always for short channel devices the current increases, so my delay would be less. So I can simply say that the third statement, that this logical effort of a two input NOR gate in long channel current model is greater than the same in the short channel current model, will be true from the logic that I have explained here. Okay, so the detailed explanation I will be coming in a moment in the next question, but using this logic also you can understand intuitively why it is such, why this statement is true. The final statement is logical effort of a two input NOR gate in long channel current model is lesser than the same in the short channel current model. So if the third one is true, it is obviously its opposite, it would be false. So my sequence would be true false true false. True false true false, this is the correct one. Clear? Okay, so in general, as I mentioned, for any short channel effect, the device current increases, so my delay would decrease, and as logical effort is the uh, logical effort is, can be explained as the amount of uh, more work that is needed to experience by a gate to experience same kind of charging or discharging. So I can reinterpret it as the amount of delay that a particular gate will experience compared to in the unit inverter. I can define it as the logical effort. So it's clear that if current is more, my delay would be less, and so my logical effort would be less. I can kind of say that. Okay, so I can say that for short channel the logical effort will be lesser than my long channel devices. Okay, let's move to the next question. Find the logical effort of a two input NOR gate in short channel current model. So here we'll be looking at the how it is obtained. Okay, so instead of two input NOR gate, let me derive it for an n input NOR gate, and as two input NOR gate would be a special case for it, I'll be simply substituting the value of n as 2, and I'll be getting the net logical effort. So let us look into it. Let me first draw a NOR gate. Sorry. So NOR gate is like this. It is an n input NOR gate. There are n such gates. Then there will be n MOSes. Here will be the output y, and if I consider in an unit inverter, I am considering the initial width was w, so it will be w by 2. Let me consider it in such a way. Okay, because sir has considered it in this way in his lecture, so let me keep it in this way. Let me consider it as w. Okay, so if there are n, or let me call it, there are x such inverters, x such x number of PMOSes in the stack, in the pull-up stack. So the sizes would be xw comma l, xw comma l, xw comma l. Okay, and we, while designing, we ensured that the current that is flowing here would be equal to the current flowing through an unit inverter, right, from this VDD to output node y. Okay, so my ISD for this stack, this current with xw and l and such PMOSes would be equal to ISD through an unit inverter. Okay, and I know that for short channel devices the expression is W, here for it would be xw into C oxide into V saturation, V sat, into VGS minus VT whole square divided by VGS minus VT plus VCL, critical voltage for this. Okay, and this one would be equals to WCOX. It is for the unit inverter. VSAT, shift it. Shift it. Okay, let me write it here. This one would be equals to WCOX VSAT. This is for the unit inverter one. VGS minus VT whole square divided by VGS minus VT plus V critical. Okay, so you can see that I can cut this one, WWCOX COX VSAT VSAT, this one. So what I will be left with is X and all the denominator terms. So if I rearrange it, X should become VGS minus VT plus N into VCL. Okay, and where does this N into VCL comes from? From this term. VC of N will be N into VC of each device, N into VCL divided by VGS minus VT plus VCL. So in the previous question you have seen that this V critical was 1.04 for an NMOS. For PMOS, this VCL value is around 2.2 volt. Okay, critical voltage. So my X should become, if I substitute everything, it would become my X should become finally, my X should finally become VGS is 0.7 plus N into VGS. Okay, N into VCL is 2.2. VGS minus VT was 1.7, N into 2.2 divided by 0.7 plus 2.2. Now for 2 input NOR, N equals to 2. Therefore my X should become 0.7 plus 2 into 2.2, that is 4.4. So 4.4 plus 7 is 5.1 divided by 2.9. Okay, so it would become 0.7 plus 4.4 divided by 2.9. So it would become around 1.75. Correct? X should be 1.75. Okay, fine. Okay, so X would be 1.75. Now if it was XW, and if I consider it is a 2 input NOR, so my circuit is going to look something like this. Change a different color. It's a 2 input NOR, so it looks something like this. VDD, so it was 2 into, it would be 2 into X because it's a PMOS into 1.75. so how much will be 3.4? 3.5. This one would be 3.5, and as usual it would be 1. So my logical effort, you can see if these both are connected with A, so the capacitance experienced here would be 3.5 plus 1, correct? That is 4.5. So logical effort would be G would be equals to 4.5 divided by 3, 4.5C by 3C, so it would be basically 1.5. Okay, and you can see this 1.5 is less than that 5 by 3, that is the logical effort for an long channel 2 input NOR gate. Okay, it is around 1.5 by 3 is how much? 1.66 around, and it is 1.5. So you can see that the previous statement that I made, that the due to short channel effect, the logical effort, the current increases, and hence the delay and the logical effort decreases compared to a long channel device, holds true. You can see it from here. Okay, and from here the logical effort is coming as 1.5. Clear, everyone? I hope it's clear. Okay, next question. Okay, fine. Okay, so question number 4 is given that RC is 3 picosecond, find the delay of the following combinational circuit, where value inside gate, size of gate, where C is the capacitance of unit and MOS. Okay, let's look into it. So I'll be using this circuit only. So here it is given the capacitance as this 10C, value inside gate equal to size of gate, so 10C, and as this is X, it would be X, this would be Y, like this would be X, this would be Y, okay, this would be Z, and this is 20C. That's fine, this is 20C. Let me make a bifurcation. So basically I have 4 stages. Okay, so let me note everything here. The G, so G1 would be how much? Logical effort. Logical effort is 1 for inverter, and parasitic effort is also, parasitic delay is also 1 for an inverter, right? Because what was parasitic effort? If this was my inverter, 2C 1C, so here it would come 3C, so parasitic effort would come 3C, normalized parasitic effort 3C by 3C, so 1, so P is 1 here. Okay, if needed anyone can zoom it later on and can find it. Okay, and so G is 1, P is 1, and what will be H? Logical effort. Logical effort here is C load by C device under test. So what is connected at load is X, this is X, and what is connected in the input is 10C, so it will be XC by 10C, so X by 10. Similarly here, G2 would be logical effort for a 2 input NOR is how much? It is 5 by 3. I think it is 2n plus 1 by 3. And if you need how it is coming, you can simply draw the architecture of a 2 input NOR, and it's very easy to find the logical effort. What will be the parasitic delay? If you look, it would be around how much? PMOS would be of how much it would be? 2 input NOR. It would be 2, right? 1 plus. Okay, yeah, it will be 2. And logical effort would be Y by X. Similarly, G3 would be 4 by 3, 2n by 3 for an input NOR, n equal to 2, so G3 would be 4 by 3, 2 into 2 by 3, 4 by 3. Parasitic delay would be how much? It will be again 2, and logical effort, electrical effort would be, this is Z by Y, and here G4 would be inverter, so 1, parasitic effort would be 1, and electrical effort would be how much? It is 20, so 20C by ZC, so 20 by Z. Okay, now I'll be finding the path logical effort G, which is nothing but product of individual G's. So it will be G1, G2, G3, G4. So it would come as 1 into 5 by 3 into 4 by 3 into 1, so it will be 20 by 9. And the path electrical effort would be similar, H1, H2, H3, H4, but simply for simplification everything will cancel out. Always remember the path electrical effort becomes output load by input load capacitance. Okay, so it would be nothing but 20C by 10C, so it will be 2. H will be 2. Clear? Okay, so F would be nothing but GH, So 2 into 20 by 9, so 40 by 9. Okay, and how many stages are there? If you remember, there is 1, 2, 3 and 4 stages. So, and here is 4. Therefore, my optimal stage effort, this is optimal stage effort, will be nothing but GH, that is F to the power 1 by N. It will be 40 by 9 to the power 1 by 4. How much it will come? It will come as 1.45. Clear? Now let me do one thing. Okay, fine. So now I know the minimum normalized delay will be nothing but n into f to the power 1 by n plus p, and n into f to the power 1 by n will be 4 into 1.45 plus capital P. And what is capital P? Capital P is nothing but summation of individual pi's. What was pi? 1, 2, 2, 1. So 1 plus 2 plus 2 plus 1 is 6. So this term is 6. This term is 6. This term. So it would become 4 into 1.5 is how much? 2.9. 2.9 to 5.8. 5.8 plus 6. So 11.8. Okay. So it is the max. It is the minimum normalized delay. Now I need the absolute delay. Okay. And you know how to find the absolute delay from the normalized delay. Just multiply it with the delay of a unit inverter, which is 3RC. So my net minimum delay would be, therefore my minimum delay will come as 11.8 into 3 into R into C. Okay, R into C, and I think it is given, RC value is given. RC is given as 3 picosecond. This one is given as 3 picosecond. So it is nothing but 11.8 into 3 into 3 picosecond. 9. So it is coming as how much? It is coming as 106.2 picosecond. 106.2 picosecond. Clear? This is how, if a circuit is given where the sizes of the transistors are known, if the x and y of the transistor is known, then we can find the optimal or the minimum depart delay of the whole circuit. This is how you find it. Clear? I hope it's yes. Yes. Okay. Yeah, what you are saying, please go ahead. So you are saying this one is constant, right? And you are varying this one. Okay. Okay, fine. Okay. See, if you change this one, or if you change the input or the output, what will happen? Your net electrical effort would change, right? It would either go up or it would go down. Correct. So if it changes, what will have change? Your F, which is equals to GH, would change, right? So your this term, this optimal stage effort would change. As a result, your minimum delay would change. So what we are finding is for a particular value of given input and given, for particular value of given input and particular value of given output capacitances. Okay. Okay. Okay, fine. Okay, then if no more questions, I can move forward. Okay, let's look into the next question. Okay, so how many unit inverters must be added between a unit inverter and a capacitor of capacitance 64C to minimize the delay. Okay, so what has been given to us? Already one unit inverter is present. A unit inverter is already present, and there are how many more unit inverters is needed to be inserted to drive this capacitance with 64C capacitance with minimum delay. So here are a certain number of inverters. Okay, so let me consider for simplicity the total number of inverters as n, including the already present inverter. So one inverter is already present. It has been asked how many more inverters are required to make it a minimum delay circuit with a minimum delay. Yes, someone is raising hand. Yes, Naveen. Would you like to ask anything? Okay, if there is nothing, we can move forward. Okay, so we know that delay is what? It is sum of the parasitic delays and this one, and f to the power 1 by n, optimal stage effort into total number of stages. And one more thing, I would like to add this, that when you are saying that gh to the power 1 by n into n, what does this represent? This represents that I mentioned it a little in the previous class also. This means that all the elements present is doing almost equal number of works. Okay, that's why n into f to the power 1 by n. That's why n into that n multiplied by this term is coming, because all are doing same amount of work. When all are doing same amount of work, on that time only we get the minimum delay condition. Okay, fine. So now as inverters are only present, n inverters are present, and inverter contributes to a parasitic delay of 1. So it would be 1 plus 1 plus this term would be 1 plus 1 plus dot 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 n number of times. Okay, so n times plus n into f to the power 1 by n. And what is f? F is g into h to the power, g into h, correct? So all are inverters, so this term, so g would become how much? G is 1, so 1 into 1 into 1 n times would become 1, and h would become c load by c input, right? So it is 64C, and here it is considered 1C, so it will become 64C by 1C. So f is simply 64. Okay, so it will become n, because there are n times 1 is added, plus n into 64 to the power 1 by n. Okay, for simplicity, let me keep it as f only for now. Later I will be writing, I will be substituting this f by 64. Okay, so we know this is the expression of delay, and we know, yes, yeah, please go ahead. Okay, fine. Okay, so now we know to find like this is the given equation of delay in terms of n. We know if we want to find the minimum or maximum value, what do? We take the derivative, because for any function these derivative terms are where we get the maximum or the minimum. And to check whether it is minimum or not, we take the double derivative. If it is increasing, we say it's maximum. If it's decreasing, we say it's minimum. So I'll be just doing the derivative, and I'll be saying that it is the minimum. But if you want to double check, you can simply do double derivative and see whether it is increasing or not. Then you will be able to say it is the minimum condition, but it will be the minimum condition. You, for your own satisfaction, you can go and check it. Okay, Naveen is saying something. One help this mid video screen record and send me, sir. Actually, I regularly record it and I upload it in the YouTube channel as per the NPTEL guidelines. I think you guys will get mail also. You can simply go into the channel, YouTube channel, and you can stream the video there. Okay, I hope this helps, Naveen. Okay, so okay, so now what I'll be doing, I'll be taking for minimum value of delay. What I'll be doing, I'll be doing partial derivative of delay with respect to this variable n. So I need more space actually. So it will be coming as something as this expression I'll be doing. So nf, so it will be f to the power 1 by n plus n into how much it will come? It will be coming as wait a minute, to the power 1 by n. So okay, just a minute, it will be something as 1 minus ln f to the power 1 by n plus 1, and it would be equals to 0 because it is the minimum condition, right? This is the minimum condition for this minimum. Okay, so it will be 1 plus f into 1 by n 1 minus ln f to the power 1 by f to the power 1 by n, okay, is to 0. So for simplicity, I'll be writing this f to the power 1 by n as f to the power 1 by n as rho. So it will become 1 plus rho 1 minus ln rho. You can solve it using a numerical analysis and all, and if you solve this one, you will get the value. You can simply put rho equals to 2. You will see that whether it is converging towards 0 or going to away from 0, and you can try multiple values of rho to find the value of find a value which is close to rho. And if you do this, you will get the value of rho as 3.591. okay, 3.591. Fine. And then so rho is basically what? It is f to the power 1 by n. And if you remember, I said f was how much? 64. F was 64. So I can write it as 64 to the power 1 by n. So what will be my n? I will take natural log on both sides, and so it will be n would be equals to how much? It will be ln 64 by ln 3.591. It will come near around 3.25. okay, it is 3.25. okay, now it is the total number of inverters that will give me the optimum amount of delay. But you can understand, I cannot use number of inverters in fraction, right? I can either use 3 inverters or I can use 4 inverters in the chain. I cannot use 3.5 inverters or 3.25 inverters. Sir, how to find this session in YouTube channel? So please provide the screen share with me. See, like in the NPTEL where you are seeing these lectures, here there will be like there is week 1, week 2, week 3, week 4, week 5. There is a separate one which will be giving you the recorded section one. If you go to this NPTEL website and if you click on that one, you will be finding one Excel sheet is opening where I am keeping record of all the videos and all the notes and all the students that has number of students that has been present in the class. And from there onwards, you can click the link and you can simply go and check the videos. You can check the previous week's videos also. Okay, because the videos are of huge size, like 5 GB, 6 GB and all, because these are present in 4K. Okay, so it will not be feasible to share with you, like share with you by any other means. It is better to go and watch in YouTube only. Okay, Naveen, I hope that clears your doubt. Okay, so n is coming as 3.25. 25. So now uh, I can use number of transistor as either 3 or 4. This should not give me the best delay case, that is the least delay case, but the delay would be close to the minimum delay only. Okay, so if this was the curve, so I might not get this point, I might not get this point, but what I might get is something here or something here. Okay, something in very close to the minimum values. Okay, so now let me check whether 3 will be giving me the lowest delay or 4 will be giving me the lowest delay. Okay, so for n equals to 3, for n equals to 3, my delay would be gh plus p. Okay, or I can write the p will be, what it will be, if it is 3, so my p would be 1 plus 1 plus 1, that is 3, that is n or 3 number of inverters. 3 inverters are there, so 1 plus 1 plus 1, 1 p from each. So it is not actually not gh plus p, it is that n into f to the power 1 by n plus sigma of pi. Okay, so sigma of pi would be 3, and n into f to the power 1 by n would be, there are 3 inverters, 64 to the power 1 by 3. So you will be getting the delay at around 15. Okay, you will get the value as 15. Check it, do it once, because 64 to the power 1 by 3 is 4, 4 into 3 is 12, 12 plus 3 is 15, so you will get the value as 15. And for n equals to 4, for n equals to 4, you will be getting d as n into f to the power 1 by n plus sigma ipi. So n is 4 here, 4 into 64 to the power 1 by 4 plus sigma ipi will be 1 plus 1 plus 1 plus 1, 1 from each inverter, 4 inverters, so 4. So this one I will be getting at around 15.313. You can check it by doing the calculation. Okay, so you can clearly see that for 3 inverters I am getting much less delay than, not much lesser delay than this 4 input, not 4 input, sorry, 4 inverter chain. Okay, so the question was how many, if you see the question was how many unit inverters must be added between a unit inverter and a capacitor. So initially I already had one inverter, this one I already had one inverter, and I need a total of 3 inverters in the chain. This n is equals to 3, so already one was present. Now and total number is 3, so new, how many more inverters are needed to be added is simply 3 minus 1 equals to 2. So the correct answer is 2. Okay, so I need 2 more inverters here to get the minimum delay condition. Fine, everything is clear, everyone? Yes, if anyone else has any question, you can ask it. Okay, I hope everything is clear to everyone. Okay, let's move to the next question. Next question is, what is the minimum normalized delay in question number 5? You can see I have already solved that for n equals to 3, it is the minimum delay condition, and I am getting the delay as how much? 15. So the answer is 15. For n equals to 3, it will be 3 into logical effort is 64 to the power 1 by 3 plus 1 plus 1 plus 1. So 3 plus 3 into 64 to the power 1 by 3 is 15 simply. Okay, so let me move to the next one. Okay, the normalized parasitic delay of an n-input tri-state mux is, okay, so what is a tri-state mux? Let me draw the diagram for this. It's nothing but an inverter with an additional input, third input n. It is called as n. Sorry, not n, it is called the enable. Okay, so say it is a, this is output is y, input is a, so and there is a third input called the enable. Okay, en. And when enable equals to 1, okay, output will be equals to input. It's not an inverter actually, it is what, it is kind of an it can be used to design muxes and all. Okay, so basically when enable is 1, it will pass the input. When enable is 0, is set. Sorry, I think it is a bar. I think sir has written a in the lectures, but it will be a bar because it is an inverter, right? So when enable is 1, output will be a bar. When enable is 0, it will simply hold the initial value, high state value, that it will become high impedance. And so okay, this is what an tri-state mux is. I will check, but previous meet link not in the website. I checked, it is there. Okay, but okay, let me just remind me in the end of this lecture. I will be sharing that link with you. Okay. Is my screen not visible to you guys? Naveen is asking. Can anyone else confirm that whether my screen is visible or not? SS means visible. See, I think Naveen, you have some issue with your internet. Maybe that's why it's not visible to you. Okay, but it is visible. Otherwise, I hope if you rejoin, I think it will be, the problem would be over. So I hope, but it's visible to others. Okay. Okay, let it be. Uh, Let me draw the circuit diagram for a tri-state inverter. So it's basically uh, tri-state mux. So it is basically, there will be two PMOSes in the stack, and there will be two NMOSes in the stack. Okay, so two of them will be connected with A, and here it would be enable bar, here it would be enable. Okay, so you can see if enable is 1, then this would be on, and enable, if enable is 1, enable bar would be 0, so this would be also be on. Else if enable is 0, it would be off, and enable bar 1, so it will be also off. So the load capacitance would retain the previous state. If it is CL, it will retain the previous state. There will be some leakage, and also it needs to be refreshed, and or else it will lose the charge with time. But uh, it will only be rewritten when enable is 1. Okay, now let's look into the sizes. As two NMOSes are present in the stack, so it would be 2, correct, because I want the net resistance to be R. So if it's 2, the R by 2, R by 2, so I'll get the net NMOS resistance as R. And here it would be 4, because two PMOSes are in series, so generally I need twice of the size as twice of NMOS, and they are in series, it would be R by 2 by R by 2 again R, so I need the PMOS sizes to be 4 and 4. Okay, so now the logical effort is what C is seeing. From here it will get 4C, from here it will get 2C. So here 6C is connected, right? 4C plus 2C. 6C is connected here. Okay, so logical effort GA would be equals to 6C by this capacitance, 6C by 3C of a unit inverter. So it will be 2. So for one two input sorry, an input tri-state mux. For one input tri-state mux, it is how much? It is 2. Oh, initially I thought that like n one input tri-state muxes are connected in series, so I did not do it for an input tri-state mux, but let me do it now. So for an n input tri-state mux, the circuit would look something like this. The circuit would look something like this. Okay. So everything would be, this would be 2n, this would be 2n, this would be 2n, and this is the output y. This would be n. Here it would be enable bar. Here it would be enable. Okay, and all there else would be connected. So this would be connected with this one. The NMOS connected, NMOS present here like this. So if it is A, the capacitance it is saying is how much? 3n. Okay, so the logical effort would be it is coming as 3n, but just give me a minute. How much it will be? 2n plus n. This will also be 3n. It is n and it is 2n. So n. Okay, they have asked about the parasitic delay, not the logical effort, right? So parasitic delay is understandable. 3n by they are asking about parasitic delay. P is how much? The capacitance coming here is 3n, see, and normalized is 3c, so it is coming as n. Okay guys, I think I have not got the question correctly. I will be coming back to it in the later classes, okay, because the answer is given as 2n, but what I am getting from here from this calculation is n, not 2n. So I need to check it once, and if time permits, in the last I will be discussing it, or in the next class I will be discussing it, okay, because I thought that n such tri-state muxes are involved, then it will be simple, uh, 2 for 1, so for n it will be 2n. That's why I thought, but no, here they're asking about n input tri-state mux. I saw this point now only, so I'll be doing it, solving it, and I'll be getting back to you in the next class. Okay, let me move to the next question. How is a gate size of 30 split amongst the transistor in a 2 input NOR gate? Okay, 2 input NOR gate, question number 8. So 2 input NOR gate is this. What is the circuit? Circuit will be something like this. 2 PMOSes would be in series, and the 2 NMOSes would be in parallel configuration. What will be the sizes? Sizes here will be 1, here 1, here 4, here 4. Basic 2 input NOR gate. Okay, this is ground, this is ground, this is my output Y. Now what is the capacitance that each input will be saying, say let me call this input as A. So the capacitance it will be saying is 4C due to this and 1C due to this, so 5C. Okay, and what it is mentioned that the size is 30 split amongst the transistor in a 2 input NOR gate. So this 5C is given as 30. So C is how much? C is 30 by 5, that is 6. Total number of questions you teach. So basically I teach about 9 to 10 questions, generally 10 questions that are available in the previous assignment in each session. So this is my 5th week lecture, so around 50 questions I have taught till now. Okay, okay, so C is how much? C is 6, correct? C is 6. So my 4C would be coming as 4 into 6, 24, and 1C will be coming as 1 into 6, basically 6. So my PMOS would get a size of 24 and my NMOS would get a size of 6. So it will be 24, it will be 24, it will be 6, it will be 6. Okay. So PMOS will be getting a size of 24 and NMOS will be getting a size of 6. Clear? I hope it's clear. The previous one is clear. Okay. If you think I'm going a little bit fast, please stop me, because today the questions are these topics are like this only. I can go into much more detailed discussion if you want. Just stop me if you don't understand anything. Okay. The critical path of a circuit is as follows. Okay, so what is the circuit given to us? Question number 9. Stage 1 is an inverter of size 10. So let me draw it. Stage 1 is an inverter of size 10. Its size is 10. Then output of stage 1 is connected to 8 of the 4 input NAND gates. So I have 4 input NAND gates here. Okay, and how many such connections are there total? There are 8 such connections in total. Okay, so total connections are 8. And this is stage 2. Stage 3 is what? Output of one of the 4 input NAND gate is connected to an inverter. Fine. This is stage 3. What is stage 4? Output of stage 3. Output of stage 3. This output of stage 3 is connected to the inverter. It is connected to another inverter whose output is connected to a 96C capacitor. This is 96C. Fine. This is the circuit they are asking for, and there are similar circuits in all the 8 branches. So basically it is a decoder that sir has taught in the class, right? So now he has asked us to find the minimum normalized delay for this circuit. Okay, let's look into it. Okay, so let me write the stages. This is stage 1, this is stage 2, this is stage 3, and this is stage 4. Okay, so if I write all these things, that what will be my parasitic delay, what will be my logical effort, what will be my electrical effort. Okay, so for stage 1, as it is an inverter, I know for an inverter the parasitic delay is how much? It's 1. Logical effort is 1. Okay, what will be the electrical effort? It will not be needed. Individual electrical effort is not needed, because as it is a 10, so 10C is connected here and 96 is connected here. So I can simply say that the net electrical effort capital H should be equals to 96C by 10C. So I don't need individual electrical efforts. Okay, fine. So now let me draw the circuit of an 4 input NAND gate. So there will be 4 PMOSes. Connected to VDD. Okay, and there will be 4 NMOSes connected in series. So what will be the sizes, anyone? I've told it multiple times. What will be the sizes of these NMOSes? Anyone? Yes, 4. And for PMOS, it would be simply 2. Right? Okay. So now, what will be my logical effort? The capacitance connected here is how much? 6C. 4C plus 2C, 6C. So logical effort will be how much? 6C by 3C, that is 2. Okay, and what will be my this parasitic delay? What is the capacitance connected here? Anyone? What will the capacitance connected here? Look into the stacks and tell me. We are using linear delay model. 12C, right? 4C due to this, 2C due to this, 2C due to this and this. So 2 plus 2 plus 2 plus 2, that is 8 plus 4, 12C. Correct? So it would be how much? It would be 12C by 3C, that is 4. Correct? And for stage 3, it is an inverter. So P is 1, G is 1. Stage 4, it is an inverter. So P is 1, G is 1. Simple. And what will be the this path electrical effort? It is output load, that is 96C divided by 10C. 96 by 10. Okay, but it is if only one NAND gate was connected. As there are multiple NAND gates connected, there are 8 branches, so I have to take this branching factor into account. So it would be 96 by 10 into 96 by 10C into 8 due to 8 such branches. So it would become 96 into 8 by 10. Okay. Fine. So now G would be equal to how much? GI into HI. So GI is how much? 1 into 2 into 2, 1 into 1 into HI is how much? 96 into 8 by 10. Okay. Basically, yes. 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 But see, yes, I'm telling you what is happening. I have drawn it for one such branch, right? But there are 8 branches. Here also some inverter is connected. Again inverter is connected. Yes, 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 yes. I understood the question. In the formation, it has not been mentioned, but uh, if you are not using this branch, like if you are like in the question, it has not been mentioned. You are correct. Even I was having this confusion, but actually, this is the architecture of a decoder that he is describing. And in decoders, whatever these NAND gates, branches are present at the output of each and every stage. Okay, that's why he has considered this branch factor 8. And there are some other things also called branching efforts and all. Okay, so like it has not been discussed, just he has told to consider this branching term 8. Okay, but in general there are other efforts also called branching efforts, from where we can get these terms, that how many number of branches are present. If all the branches are not same, then what will happen? Okay, for simplicity, we'll be just assuming that all these stages have similar amount of similar kind of branches, and that's why this 8 term has been taken into account. Clear? Okay, but you are right, in the question it has not been mentioned clearly that all this, it has only been mentioned, see, one of the four input it has been mentioned, like only one has such kind of branches. Okay, but what he is intending the actually, because otherwise you will not get the correct answer, the answer will be deviating. I tried it, that one, I thought why it is deviating, then I thought understand that the formation of the question is not apt. So uh, that's why we have to use consider this branching effort terms also, this branching term also. Okay. Okay, Naveen is asking something. No, Rohit is asking something. Hi sir, NPTEL week 5 assignment, answer me sir. I cannot answer you the this time's assignment, I cannot give you the answers. We have been strictly instructed just to solve the previous year's assignments. Okay, Rohit. But I think you'll be able to answer them easily, because if you have gone through these videos, if you have gone through such lectures and these videos, then it won't be a problem to solve them. Okay. Yes. 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 Yes, but then we will not see. uh, I've shown it for simplicity, but if you don't consider them, then this term, this 8 term, this branching term will not be taken into consideration. Okay, because why the net. Yes. No, no, go ahead please. Yes. See, actually, what is happening, for all these 8 cases, for all these 8 branches, there are some output load capacitances connected here. Okay, and as all these are connected in parallel, the net capacitance would be sum of all these capacitances. You can think it in this way also. So the net C would be sum of as these are in parallel, sum of all these 96C capacitances, 896C capacitances. So it would be 96C into 8. From this part I am getting this 96 into 8 term. Okay, actually what is this delay that I am trying to drive through this inverter, I am trying to charge the output load capacitances. Okay, so if output load capacitances are connected to multiple branches, this will also have some effect on it. And as all of them are similar, so I can consider them to be all of them to be the critical paths, all of them are contributing equally. So that's why this 8 term has been taken into consideration. Okay, so now GH will be coming as how much? GH is coming as 2 into 96 into 8 by 10. Okay, this is the overall path effort, and it will solve it, it will come as 153.6. Okay. This is the overall path effort. Okay, now how many stages are there? 1, 2, 3 and 4. 4 stages are there, therefore n equals to 4. Therefore for 4 stages, f to the power 1 by 4 is how much? 153.6 to the power 1 by 4. How much it is coming? Let me do it. 143, sorry, 153.6 to the power 1 by 4. coming as 3.52. 3.52. Okay, now delay would be how much? N into f to the power 1 by n plus summation of these parasitic delays. So n is 4, 3.52 plus this parasitic delays. Now what was the parasitic delays? It was 1 plus 4 plus 1 plus 1. So it is 4 plus 3, 7. 1 plus 1. So it would be how much? 4 into 3.52 is 14.08 plus 7. So it is 21.08. So is 21 an answer? See, 21 is an answer here. Correct? Any confusion? Okay, fine. This is how you solve such kind of branching effort. This if multiple branches are present, this is how you solve, how you approach to solve them. Okay. Okay, the last question of the day. While optimizing the circuit for the number of stages, the value of f to the power 1 by n should be close to. I have already done it, but let me redo it once again. I have done it for only inverters. Now for any general circuit, what happens? Say I am having a general circuit like this. Here it can be anything, NAND gate, NOR gate, anything can be there in this circuit. Okay, and I have a chain of inverters or a chain of buffers, anything it can be. Let me consider a chain of inverters. Okay, and the total number of gate is how much? This is my input. Total number of gate is, let me consider it as n, and the number of gates initially present was n1. Number of stages was initially n1. Okay, so number of inverters is n minus n1 here. Correct? Now what will be the delay? Delay would be n f to the power 1 by n plus pi and gh for this one, gh. So it would be n f to the power 1 by n plus I pi. G is how much? As inverters are present, so electrical effort would be 1 and G would be n minus, sorry, G would be 1 and H would be n minus 1. Okay, so now again I will be taking the partial derivative of this delay expression with respect to n, and I would equate it to 0. Okay, so let me take the derivative. What it will become? Okay, first this one. So f to the power 1 by n would become f to the power 1 by n ln f, and 1 by n would become minus 1 by n square plus f to the power 1 by n to the power 1 by n, because derivative of dd or n of dd and n of n is n1, plus this term would be of no significance, it is constant, it will cancel out. Okay, and n minus n1 would become 1 minus 0 plus 1 minus 0. And one more thing, if you remember, in Elmore delay model and in linear delay model, there was some difference in the delay, right? This parasitic delay was coming different. That's why we said that we should limit our number of inputs to 4 or 5. We should not go beyond 5. Not even 5. Generally, stay within 4 inputs are fine, 4 input is fine. So as there were some difference in delay, but still why we are using this linear delay method. This is because in optimization problem, this parasitic delay term is a constant and it gets cancelled out when it becomes 0 when you take the partial derivative with respect to n. So this delay optimization session problem will not be affected whether I am using Elmore delay model or a linear delay model. Okay, that's why using linear delay model is also fine until and unless you ensure that the pi, the difference between them is not significant. Okay, this is the reason. Okay, so now this one would be equals to 0. Why? 0 is for minimum condition or maximum condition. If you take the double derivative, if you see it's increasing, then it's for minimum condition. Okay, you can do it and you can check it also. Now if I simplify it, it becomes 1 plus f to the power 1 by n, 1 minus ln f to the power 1 by n to 0. Again let f to the power 1 by n as rho, so 1 plus rho 1 minus ln rho is 0. If I solve it numerically, I will get the value of rho as 3.59. The question was, while optimizing the circuit for the number of stages, the value of f to the power 1 by n should be, what we are getting is 3.59. okay, and it is not needed here, but from this we can find it as ln. If I solve it, I will be getting ln f by ln 3.59, and I am calling it is actually best number of stages, like number of stages that will give me the least amount of delay. How to find this meeting screen record video on Google? Okay, Rohit, you are having the same confusion. In the NPTEL video lecture series where sir is uploading, you will see that there is another below the weeks, week 1, week 2, week 3, week 4, week 5, week 6 and so on. Below them you will find there is another link which is for these recorded discussion sessions. You can simply join there. Okay, and you can go to that link. You will find that one Excel sheet has been opened. In Excel you will find the individual YouTube video links of all the lectures that has happened till now, and you will be finding all the documents in PDF format as well as number of students that has attended the lectures. So you can go there, and I think I have to check that link. Just give me a minute. I think I have to check the link. Let me check. Give me a minute. Sent items. Okay, here is the link. Okay, I will be sharing with you the link. Okay, did any of you guys receive any mail regarding this? I think you have received it because I have also received it. That from NPTEL team you must have received a mail regarding the links. Can anyone go and check that whether it is available or not? Because 2-3 weeks back I checked it, it was there. You can go and simply check. You will get the link there. That the link will contain all the YouTube videos. See, like others have also checked. You kindly go and check there. You will be finding the videos there. Okay, Rohit. I hope it is clear. Okay, so there are only 10 questions, and that one question regarding that I have to think a little bit. That tri-state mux, the normalized parasitic delay of an n input tri-state mux. Just give me a minute. Let me try to think it. If the answer is coming, that's fine. Else I'll be discussing with you in the next week about this one. 3n 2n. Plus n 3n. Yes, please go ahead. Okay, go ahead, tell me. Sure. Okay. Okay. Two input NOR gate, which is sized to be 4:1. Okay. So NOR, right? So this is the sizing that they mentioned, correct? So what are the capacitances connected here? Elmore delay model, they have said, not linear delay model. Okay, so there will be some capacitance connected here also, 4C, and here also, here it will be 1C 1C 2C plus 4C 6C, correct? And they have told falling, right? So you have to consider this capacitance also. Have you considered this one while solving it? Do For falling, do you need to consider? I have to think on it. um, yes, for rising you have to consider this. um, See, for falling also you need to consider this 4C. You know why? There might be condition where, say, this one is 0 and this one is sorry, this one is 0 and this one is 1. Fine. So in this case what will happen? This one will be off, but this one would be on, right? So you need to discharge this one also along with this two. Along with this one you have to discharge this capacitance also, correct? And what I said, that this propagation delay is the worst case delay. If you are finding the contamination delay, you don't need to think about this one, you don't need to think about this one in contamination delay. But in propagation delay, you have to consider that this capacitance is also needed to be discharged. And I think you have not considered this one, that's why your result was deviating, correct? Yes. So for, yes, tell me please. So now what, it will be simple RC. See, it would be R and 6C, and here you will get one more R, and you will get one more C, 4RC. Now find this Elmore, using this Elmore delay one, find the circuit, solve it. Yes. Give me a minute. R by 2, it is R, and yes, it will be R by 2, correct? So solve it, I think you will get it. So how much it will come? 6RC plus 3R by 2 into 4C, something like this. 6, so it will be 12RC, something like this. Okay. Okay. Oh yes, no need. Even I have forgotten this Elmore delay method. Yes. So 8 hours. It is how much? It is 4. So 4C plus this one, because this is my output node, right? So only R will come into picture. R by 2 will not come into picture. So yes, it will be like this only. 6RC plus 4RC. So 10RC. Okay. Okay. Yes. Okay. NAND gate. So fine. Propagation delay rise, right? Propagation delay rise. Okay. So the sizing would be NAND gate. Sorry. So it will be 2 2, it will be 2 2, fine. And you need to find the propagation delay, so rising. So it will be same, the capacitance here will be how much, 6C. How much here, 2C. Okay, so your it will be something like this, R into 6C, and it will be R by 2 into 2C. Here it is the output. So again R into 6C plus R into 2C, so 8RC. Okay, most welcome. Fine. Anyone, anything else? Please go ahead. Okay, yes. It will be simple, like, see, for any circuit, see, you will not be dealing with NAND gates and NOR gates when you will be going to circuits. Okay, this NAND gate and NOR gate architecture only comes in memory stacks generally, uh, or even in some decoders and all. Okay, you will be dealing with multiple circuits. So the general approach is, for any circuit, we will be ensuring, the first step will be to ensure that the rising delay and falling delay are same. How to ensure it? If there are n number of transistor in a stack, in an NMOS, go, the sizes would be n times the size for an inverter, that is n. For PMOS it is there, the size will be twice of what PMOS has, and we have to ensure that the resistance are equal in the pull up network and pull down network. Okay, so this is the first step. Then what we'll be doing, will be accordingly we'll be finding the capacitances, find capacitances. Okay, then solve the propagation delay for rising or falling. Okay, for rising and falling, generally for your calculation you can use Elmore delay model, but while circuits do it, while we do spice simulation in circuit, what we do, say I'm making a new circuit. Okay, I'll be designing the circuit, I'll be writing the netlist either in spice, some softwares like HSpice or Inspector, or I'll be drawing them in Virtuoso. I'll be doing them. After doing what they do, they don't use Elmore delay model. Okay, because you can see n square terms are there, so it will be much more time consuming. They use linear delay model or other models, and they solve the equations using them. They do similar kind of approach, take the resistances, find the capacitances between each nodes, and they solve the equations. Okay, and so what you will be doing, if Elmore delay is given, just find the ensure resistances are equal, find the capacitances for this corresponding sizing, and then solve for TPD, the propagation delay rise or fall, either by like Elmore delay or linear delay model, which one has been asked or which one suits you better. Okay, so for NOR gate, NAND gate, anything, just follow these steps and you will get the answer. Okay, okay, you try it once, it will be easy, it will not be difficult. Yes. Yes, it will vary. Yes, it will vary. And why it will vary? Because in Elmore delay model we have considered this resistance, these capacitances, but in linear delay model we have neglected it. And why it's okay to neglect them? First of all, we, while designing circuits, we ensure that that the number of input does not exceed 4 or 5. If you see the Sir's lecture, he has also explained that when it is around 4 or 5, the difference is not significant. Okay, beyond 5 it becomes out of control, but generally we limit it to 4. Okay, 3 or 4 is fine. With, even if you use 4 input gates, the difference between Elmore delay and linear delay will not be significant. Second of all, during this optimization problem, these parasitic delay terms, where this Elmore delay affects the difference, they get cancelled out due to taking derivation, partial derivations, and it is independent of n, the number of stages, so they get cancelled out. So that don't affect our delay optimization problems. Okay, so that's why using both Elmore delay and Elmore delay model, substituting the Elmore delay by linear delay model or other models which are fast in computation, because when you are running the circuit, we don't want the we want instant outputs, right? Even when we do complex circuit simulations, it might take hours to run them. We use stacks of thousands, like 128 cross 128 cross 128, or like in memories what I do, it can take hours. And if this Elmore, if Elmore delay model has been used, it might take tens of hours to run it. Okay, because n square, you can see, understand how many more calculations it is needed, because they need to find n square instead of n. Okay, and if more complex circuit is present, like it will go out beyond control, the delay would go. So we want fast calculations, so we substitute this portions where n square term or higher terms are available with linear terms, and we ensure that the difference is not significant. If I am getting a delay of 3 picosecond in 10 minutes of simulation time, and if I am getting 3.12 picoseconds in say 50 minutes of simulation time, I would prefer this one, right? Because I'm getting the simulation result faster here. So this is the idea. Not actually 3.1 second, it is much less, like 3.01 or 3.07, something like this. Okay, so that's why we generally use these linear delay models to solve these delay problems, circuit delay problems. Is it clear? Okay, fine. And yes, yes, logical effort. Okay, sure. Tri-state mux, right? Okay, see, this is easy. Actually, tri-state mux has been kind of tri-state mux has been kind of derived from this one, this circuit. So it is my tri-state mux, correct? This is VDD, this is ground. So what will be the sizes? Here it is enable, here it is enable bar, 2, 2, 4 and 4. Okay, what you are asking is tri-state mux. Okay, I forgot the architecture for tri-state mux. Just help me. Just help me. Okay, give me a minute. Let me see the architecture of tri-state mux for once. I don't want to be wrong. Tri-state mux. Okay. Tri-state mux is little tricky to handle. Like this, right? You will get another input here like this. This is your tri-state mux, and when you break this tri-state mux, we get tri-state inverter. That was what I was going to tell you. Okay, so tri-state mux logical effort you cannot find directly. Just give me a minute. I found it out once. Let me find it. Did sir already teach you tri-state mux? Tri-state inverter. Okay. Okay, fine. So this is your tri-state mux. And is there a feedback also present here like this? feedback is not present. Okay, see, uh, this is, if this is the tri-state mux, the problem will not change because the capacitance will be same, it will be 6C only, correct? It is 6C. How much is the output? We will say it is also 6C. So what will be the logical effort? This one 6C divided by, for an inverter 3C, so it will be 2, correct? Okay, actually I don't work with this like digital circuits a lot, so I have to look into the circuit, what is actually a tri-state inverter. I forget these things. I have to check it once, what is the architecture. Once you, like, there are multiple circuits, majority gates are there, so many Toffoli gates, there are so many varieties of circuits that you have to work with. You just need to understand the basic how to approach this problem. The idea is, yes. Select lines are not inputs. Okay, so do you remember that once I talk about this transmission gate? What was transmission gate? Transmission gate was like this. Okay, this is called an wired OR. If it is y1, it is y2, then it is y is actually, it is called y1 wire or y2. Fine. And this is called, these are the select lines, s1 s2, and this one, these are select lines. So these are select lines basically. Okay, like when you design mux, there are select lines. This is what it is being represented here using transmission gate logic. Okay, so what they are saying is this S is the select line, not inputs. Okay, here I think this one will act as the S, and they are saying it will be my select line, not the input. This is what they are meaning. Okay, if you solve this circuit, you will if you redraw it, you will get something like this. Okay, that's how actually what happens when you are trying to characterize a circuit. When you are trying to characterize a circuit, we need a driving circuit at the input, and generally we use inverter as a driving circuit. Fine. Now if I want to analyze a transmission gate, this is my transmission gate. Okay, this is my transmission gate, this one, it is my transmission gate. Now to uh, to understand it, to characterize it, I need a driving circuit here, and that's why I'm using an inverter, unity inverter. Okay, and when, like, what is this circuit? If I redraw this circuit, I get something like this. If I redraw it, I will be getting something like this. There will be a PMOS, there will be an another PMOS, another NMOS, another NMOS. Okay, NMOS. Here it will be connected, they will be connected. This is basically this circuit. Okay, and here it will be, it's A, it will be A, this output, it will be output, and whatever was going here, say it was D0, it was D0 bar, so it will be D0, it will be D0 bar, this one. Okay, now if I break this one, because it is difficult to analyze, what I will get is, I'll get this circuit that you have seen till now. This is what we are getting. So when we are analyzing this circuit, basically we are analyzing a transmission gate driven by an unit inverter where the out feedback has been taken off. Okay, so this is the basic idea behind this circuit. Yes, it will not take a significant, it will not make a significant change. The only difference it is, if feedback was present, the delay would have been little different. Okay, because there is feedback path present here. So now the delay will be changed, but for understanding and for analyzing, we break this feedback path. It is much more easier to analyze this circuit. Okay. 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 Yes, ask it where it is. Yes, yes, please. This one. Yes, I think this is wrong, because I think this one would be correct. Sure, sure. Yes, yes, like this. Okay, that is the confusion. Like when I did the, like when I did for rough, what I did it for one input. Okay, then I cascaded n such gates. On that time, what will happen? Simply, my parasitic delay is n. Parasitic delay for one is coming how much? What will be coming? It will be simply multiplied by n. So I will be getting 2n. That is how I was getting. But now I am not sure whether simply cascading it n times would give me the answer, or I need to use such kind of architecture. I'm not sure about it. So I have to check into the papers, or I have to check into check into this architecture of an input tri-state mux. Then I'll get back to you. That is what I was saying, because I'm not sure what is the actual structure of an input tri-state mux. Okay, I have not seen the lecture actually. So what did he say? That it is simply cascading of n such gates, like these. Oh, then it's simple. Like then it's correct only what I did. Okay. Then for one it is coming as two. For one tri-state mux it is coming as two. For n such, how much it will come parasitic? It will be simply added, right? So it will be two n times. So it will be twice n. So 2n will be the correct answer. That is what I did. But now when I was reading this question, that n into tri-state mux, I was confused whether such kind of architecture exists, or this has been cascaded n times. So that was the confusion I was having. Okay. Yes, this one. Yes. Okay. Okay. Yes, yes, that's fine. That is what actually I thought while I was doing it. But now when I was going to solve, I don't know what clicked in my mind. I thought that such kind of architecture might exist. I'm not sure about it. So I thought it is better that I go and see the papers what actually an input tri-state mux is. That's why I told that I'll be talking about it later on. But yes, as you have clarified it, what's even Sir has told it, as you were saying, that it is an one input tri-state mux. So n such circuits will be connected n times. So there will be an n input tri-state mux. So simply for one, it is parasitic delay is coming as how much? It is coming as 2, right? Because it is 6c, and that is also sorry, it is how much? 6c by 3c. So 2. So for n inputs, it will be coming simply as 2n times. So it will be 2n. So 2n is the correct answer. That is what even I have thought while I was doing it. Thank you for the clarification. Okay, fine. So this is wrong. Rub it. Okay, fine. So anyone else has any question? Okay. Hi sir, link. Okay, Rohit wants the link. Okay. Just give me a minute. Let me find it. Sent items. Okay, found the link. Come on, see. Check the link once. I've sent it. You can go and check in the link. I think it will work. Sorry, I have sent you the wrong link. Sorry, I have sent you the wrong link. Just give me a minute. Not this, not this. Not this link, this link. Okay, fine. Yes, this is the link. So check this one, it will work. And the previous link, don't use it, it is for us. There is nothing special, but the latest link that I have shared, you will get all the videos there. For asking, can you please teach the RNC calculation again for any model if time permits? Okay. Like what, Uttra, what do you want to ask? Like logical effort calculation? Okay. Let me do it for a 3 input NAND gate or 2 input NAND gate. Will it suffice? Can I do it for 2 input NAND gate simple circuit? Will it be sufficient for you to understand it? Okay. Not neither your nor mine. Let me go for a 3 input NAND gate. Okay. Okay. See. NAND. So it will be in parallel PMOSes. What will be the sizes? It will be 2, 2, 2. It will be how much? 3, 3, 3. Okay. This is the. So what I should do? N input NAND gate, N input. Okay, 4. Fine, 4. Into. So it will be 4, 4, 4. Is it fine? Okay, see. So what is the capacitance that input A will see here? How much it will be? It will be 4C plus 2C, 6C. And what will be the output capacitance here? 2 plus 2 plus 2 plus 2, that is 8 plus 4, 12C. A linear delay model, correct? So what will be my logical effort? What it is? It is the capacitance seen at the input. Okay, how much it is? 6C divided by capacitance of an unit inverter, correct? It is 2. And what is the parasitic delay? It is the parasitic delay will be the capacitance seen at the load, that is equals to 12C divided by capacitance of an unit inverter, so 3C, so it will be 4. Clear? It's better. In the previous class, I think I did it for an N input NAND gate. I think I found out the logical effort and all. You can go and check that video also. If it was N input, what I will do? I will simply make the circuit sizes as N. Okay. Then I have to solve it. If you remember, I solved it using, I think, arithmetic progression. And if you solve it, you will get the value as the desired expression for logical effort and parasitic effort. You will get it. Do you remember that one? Week 4, I think I did it. Check. Yes, I did it. It is there. I did it for Elmore delay model, and for logical delay model, for logical effort using a linear delay model, it should be much simpler than Elmore delay model. Okay. Just understand how it is done. Just understand how it is done. Rest, everything is same. Everything is simple. Just understand the approach. What is logical delay? What is logical effort? What is parasitic effort? What is electrical effort? So delay is basically what? P plus GH. What are the expression of G and H? Remember, try to understand that. Okay, from where it has been derived, this P plus GH term, from where it is coming, try to get that expression. Then you will understand what is the effect of G and H, and then you will never forget this. What is G, what is H, what is the significance of P, what is the significance of H, and what is the significance of G. Try to understand that. Then if you, once the concept is imbibed in your memory, once you understand the concept, then it will not be problem to like find the G and H for any circuit. Okay. Okay, most welcome. I hope everything is clear to all of you guys. Okay, then we can call it a day. Sure. Okay, best of luck. See you next week. Okay, let me end the meeting. Bye. Bye. Okay, most welcome.